Welcome to this explainer on the energy potential of wastes. Today, we're diving into the MEN 313 module, authored by your class instructor, Engineer Val Irvin F. Mabayo. We're going to tackle this material exactly how a university master's student should, zeroing in on the foundational concepts that actually bridge the gap between everyday waste generation and true energy recovery. Let's get right into it. Here's our roadmap for the session. We'll be moving through waste and the circular economy, characterization, the crucial bridge, analyzing physical and chemical properties, assessing biological energy potential, thermal versus biological pathways, and we'll wrap up with engineering judgment and suitability. Section 1, Waste and the Circular Economy. Let's start by figuring out exactly where waste to energy actually belongs in the grand scheme of sustainable environmental engineering. Before we even start talking about energy recovery, we have to recognize that in a circular economy, our absolute primary goal is retaining material value. We're engineers, right? We shouldn't just look at a massive pile of municipal solid waste and immediately think, let's burn it. Our very first instinct has to be reduction, reuse, and recycling. Because of that, waste to energy has a highly specific, fundamentally limited place in the hierarchy. It's a tool we use only after all those higher value material recovery options are totally exhausted. It's essentially a solution for residual waste, those complex, non-recyclable fractions that would otherwise just sit in a landfill pumping out methane. Section 2, Characterization, the crucial bridge. Now that we know our boundaries, we have to flip our mindset. We aren't looking at waste as a disposal problem anymore. We're analyzing it as an engineering input. And here's the kicker. Just because you have an abundance of waste doesn't mean it's suitable for energy recovery. A city producing thousands of tons of garbage a day isn't automatically ready for a reactor. We have to evaluate that material rigorously as a feedstock. That makes waste characterization the absolute crucial bridge between a municipal headache and a viable, project-specific engineering solution. Honestly, this is the 20% of upfront effort that will dictate 80% of your project's success. Without characterization, you are literally flying blind. So, how do we evaluate this feedstock? We applied the Socratic method. And the very first incredibly critical question we have to ask is simply, how wet is the material? That one detail immediately starts filtering our technology options. And we follow that up right away with, is the supply stable? Is it reliable enough in both quantity and quality to justify building a long-term, multi-million-dollar facility? A highly energetic waste stream that only pops up a few months out of the year is completely useless for a power plant that needs to run 24/7. Answering these specific characterization questions directly dictates our entire waste-to-energy technology selection. It's a pure cause and effect relationship. Think about it. If you don't know the ash content, you can't design the residue management system. And getting that wrong, that leads to a catastrophic failure of the plant. Section 3, Analyzing Physical and Chemical Properties. Let's zoom in on the exact metrics you're going to be testing for in the lab. Like we touched on earlier, water is the enemy of direct thermal conversion. High moisture drastically tanks your useful heating value, mostly because you end up wasting a ton of your fuel's energy just evaporating the water before any actual useful power is produced. To put that into perspective, take wet wood sitting at about 50% moisture. Its heating value is substantially lower than completely dry wood. Two pieces of the exact same material will perform radically differently if one was left out in the rain. Moisture content can actually dominate fuel quality way more than the underlying waste category itself. Beyond moisture, you've got chemical properties like ash content, chlorine, and sulfur. These are absolute deal breakers. They tell us if a waste is going to destroy our reactors. Slagging happens when ash melts and coats the inside of the combustor. Chlorine combined with water vapor, that creates literal acid rain inside your pipes. You have to know these properties beforehand, no exceptions. Section 4, Assessing Biological Energy Potential. But what happens if our characterization comes back and we have a really wet, organic-heavy waste stream that completely fails the thermal tests? We definitely don't just give up and send it to a landfill. In that scenario, we pivot. We start looking at biological properties. We want a high biodegradable organic fraction, and we absolutely need an absence of inhibitory contaminants, because those will kill our microbial cultures. We are shifting our whole paradigm from high-temperature burning to microbial digestion, balancing nutrients to make sure the bacteria thrive and produce biogas. Section 5, Thermal versus Biological Pathways. And now we've hit the critical junction. the data is forcing us down one of two fundamentally different engineering routes. This is the core cause and effect relationship for this entire module. The physical properties dictate whether we use high temperature oxidation for dry wastes or microbial digestion for wet organics. You just cannot efficiently force a wet, sludgy waste into a gasifier. And you certainly can't feed dry, inorganic plastics to a tank full of bacteria. The feedstock properties make the decision for you.
Now, if the thermal route is chosen, we don't just broadly incinerate things. We have to carefully, deliberately match the exact technology, from mass burn all the way to advanced gasification, to the precise moisture and heating values we measured in the lab. Gasification, for instance, requires way tighter control over particle size and homogeneity than a standard mass burn grate system.
Section 6, Engineering Judgment and Suitability. Finally, we have to synthesize all of this raw data into applied engineering judgment, because honestly, data without synthesis doesn't do us any good. Remember, suitability isn't some universal given. A high-moisture food waste is a uniquely terrible direct fuel, but it's an incredibly good candidate for biogas production. Your job as an engineer is to find that perfect, specific pairing between the waste's inherent properties and the reactor's strict needs. To make that judgment correctly, you've got to follow a sequential methodology. Classify the source, identify the composition, explicitly screen out those recyclables, measure your properties, and only then do you match it to a pathway. Skipping steps here, like jumping straight to picking a technology before checking for recyclables, is exactly how projects fail. Engineer Mabayo notes something essential here. Your role isn't just to generate power. Your role is to ensure the entire system protects public health and the environment. We aren't just solving a straightforward energy problem. We are solving a highly complex environmental systems problem. So, I'll leave you with this final, absolutely vital question to consider as you go out and design these systems. If a city builds excess thermal capacity, will it create pressure to burn materials that really should be recycled? Are you oversizing your facility and accidentally cannibalizing the exact circular economy we are trying to build? By truly understanding waste characterization, you can right-size your facilities to ensure they only process true residual waste. Thanks for hanging out with me for this master's level explainer. Keep questioning the data and stay curious.